start moving into rates of change. Rate of change is a fancy word for slope. Section 4 is rates of change, tangent lines, and sensitivity. So what we're going to do today is start by exploring slope the way we learned slope back in the day. So it says find the equation of the tangent line to the parabola y squared, y equals x squared at the point 1, 1. So in order to find the tangent line, what we're going to do is to approximate the slope by choosing a point near 1, 1 on our parabola. And we're going to call that slope the secant line. So the slope of the secant line, or PQ, is made up of the equation x squared minus 1 over x minus 1. X squared because that's my function, minus 1 because that's initial point, x minus 1. So what is the slope if I pick my point to be 2, 4? Because again, if x equals 2, y equals 4, then the slope of PQ would be equal to 4 minus 1 over 2 minus 1. What? No. This is x. This is y. The original, so the x squared is coming from y equals x squared. So technically this is like y minus 1. Correct, because that's not that 4 is equal to x squared. Like I already plugged it in. Think about this, it's x comma x squared. Because it's typically x comma y, but y is equal to x squared. Yes. What? No. No. Okay, plug in your next 2 points. So what are we doing with these points? What's happening to my x values as we continue to look at these points? Yes, and closer to what? Yes. So here we started at x equals 2. Now we're at x equals 1.5. Now we're at x equals 1.1. And what's happening to our slope? It's getting closer and closer to 2. So that should suggest that the slope of the tangent line should be in general, we say that the slope of the tangent line is the limit of the slopes of the secant lines, which is what we're going to talk about today. So in this problem, that would mean that the slope of the tangent would be equal to the limit as x approaches 1, which plays. Now you can do what you want to do, because if you plug in 1, you get 1 minus 1 over 1 minus 1, which is 0 over 0, which means to find our limit, we have to do x minus 1, x plus 1 over x minus 1, which means we have the limit as x approaches 1 of x plus 1, which gives you 1 plus 1, which gives my limit equaling 2. To find the equation of a tangent line, we use the given point and our slope. So if you have a point and a slope, what equation from algebra are we going to use? Yep. So you plug into point slope form. That's my y1. My slope is 2. There's my x1. And this is the equation of the tangent line at the point 1, 1 of y equals x squared. Yes. Sure. Okay, so the graph is x squared, right? So there's our function. Now what we're doing is we are looking at our function closer and closer and closer to the point 1, 1. So the tangent line, which I have to get this into point slope form. Is 2x minus 1. So what that means is that on the graph, the tangent line will go through the point 1, 1, and this line is representative of the slope of the curve y squared at the point 1, 1. Does that help? There you go. Yes. To like get that line like I just typed in? No. Your calculators are smart, but not that smart. Your calculator can find the value of the slope, but it wouldn't be able to give you the equation of the tangent line. So like in here, this would find the value of the slope, change in y over change in x. So like you could type in x equals 1 and you'd get 2. But on a test for me, this would be a non-calculator question. Okay. That leads us into today's lesson. All right, rates of change, tangent lines, and sensitivity. So what we're going to do today is use limits to determine instantaneous rates of change. So like I said, 1.4 directly relates back to 1.1. The very first thing we started talking about when we started talking about chapter 1 was average and instantaneous rates of change. We are going to continue looking at that today, but on a much more involved level. So the amount of change of a quantity over a period of time is known as an average rate of change. The amount of change of a quantity over a period of time is known as average rate of change. The change in the interval over the length of that interval, aka a more in-depth look at slope. Change in y over change in x. Average rate of change is good old slope. Average rate of change is good old slope. All right. Find the average rate of change of x cubed minus x over the interval 3, 1. So average rate of change is equal to f of 3 minus f of 1 over 3 minus 1. Change in y over change in x. So 3 cubed minus 3 minus 1 cubed minus 1 all over 2. So 3 cubed is 27. 27 minus 3 is 24. 1 minus 1 is 0 over 2, or 24 divided by 2, which is 12. So the average rate of change of that function over that interval is 12. We can also describe rates of change by looking at slopes of secant lines. That's what we did in our warm-ups. So we looked at the slope of several secant lines, trying to approximate the slope of the tangent line. So the slope of a secant line is considered the slope of the secant, or f of x2 minus f of x1 over x2 minus x1. A secant line is the same as the average rate of change. So in calc, the more fancy word is the slope of the secant. The slope of the secant represents the average rate of change. The slope of the secant represents the average rate of change. The slope of the secant represents the average rate of change. The tangent is equivalent to the instantaneous rate of change. A tangent is the equivalent of the instantaneous rate of change. It is the limit of the slope of the secant. It is the limit of the slope of the secant. So the secant line touches the curve at 2 points. And it was hard for me to show you that on the graphing calculator. What's more easy to show you is down on the example on this page, because I could post lines. So we're going to look at almost what we talked about in the warm-up on the next diagram, even though the functions are different. So a slope of a tangent line will touch the curve at 1 point, where the slope of the secant line touches the curve at 2 points, hence x2 and x1. So let's look and investigate that graphically. So this curve right here, the black curve, that's your function. And then the purple and the green are the tangents and the secant. The tangent line is the curve that touches twice. So this line right here is the slope of the secant. That is the PQ. It touches the graph twice. The tangent just like on my graph on my calculator, hits the graph once at the point in question. So that red line represents the slope of the tangent at x equals a and only a. The slope of the tangent at a different point at this a plus h would be different. The slope of the tangent at that point is different than the slope of the tangent at this point. The slope of the tangent is constantly changing with the graph. So we approximate the slope of the tangent using the slope of the secant. We find the slope of the tangent by looking at the limit of the slope of the secant. So in general, down at the bottom, you can put these two formulas. The slope of the secant is equal to f of a plus h minus f of a all over h. Just like in our previous study, we are trying to get h closer and closer to 0. Just like in the warm-up, I was getting that denominator closer and closer to 0. So if you flip back and you look, the denominator went from 1 to 0.5 to 0.1. So the denominator, as we looked at 3, 4, and 5, was getting closer and closer to 0. Yes. Yes. Everybody. All right, so a biologist would use this type of activity to look at rates of change of population under controlled conditions in a lab. We could use this with fruit flies. Fruit flies are like those obnoxious little things that you might see one and then all of a sudden there's like 100. So what we want to do in this example is use the 0.23150 and compare its average rate of growth with another point on the graph. And the first point we're going to compare it to is 45,340. So we're going to look for the average rate of growth, aka the slope of the secant line, using the 2 points, 23 and 45. So we have 340 minus 150 over 45 minus 23, which means that there were 190 new fruit flies over 22 days, which on average is 8.636 fruit flies per day. So from day 23 to day 45, we added 190 additional fruit flies. So the average rate of change is a growth of 8.6 fruit flies per day. What we can do is look at the population growth and predict how fast the population was growing on day 23. So what we want to do is decrease the change in from 45, because this to this, does that line drawn in look like it's very good at approximating the slope at 23? No. So what we want to do is create slopes closer and closer to 23. So maybe we investigate the point 30. So we could look at the slope of the line from 23 to 30 At 30, it looks like there's about 260 flies. Yes. So we have 260 to 30. So 260 minus 150 divided by a change in 7 gives 15.714. So we can see that that average rate of change is almost double the rate of change previously. So what that tells us is that the rate of change or the growth in the flies over that 7-day period was much greater than the rate of change over the 22-day period. Let's get even closer because still that slope isn't that great. So let's look at day 25. Day 25 looks to be about 180. Oh, just kidding. Sorry, I thought it went by 25. I would say probably closer to, since it's so high up, 190. I'm just going to make your slope a little steeper. And so now that's about a slope of 20. So much steeper and probably closer. You could also look at the slope of the secant for a point below. So if we looked at 25 to 23, we could also look at 20 and compare it to 23. So at 20, it looks to be at about 100. So you get 16.666. So it is fair to say that the slope of the tangent between those 2 points is probably somewhere between 16 and 20. So the population on day 23 is growing at a rate of, and again, you could just pick in between those 2 points. So maybe like 18.5 fruit flies per day. And again, you can't come up with an exact because we don't have a function and we don't have exact points. If you had exact points on the graph, then you could be even more close. But if this were the case, you're approximating, they're approximating. You know, Corey might have picked 185 instead of 195, so his 20 might have been down a little bit, etc. In example 2, it says find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. So we already did that. We found that in our warm-up. So we found that the tangent line was equal to y equals 2x minus 1. What we're going to do now is actually find the slope of the tangent using the limit as h approaches 0 of the slope of the secant from that same example. So we approximated or predicted what we thought the slope of the tangent was. So this was our guess from the warm-up. What we're going to do now is find it actually. So if you think about our formula, the slope of the secant is equal to f of a plus h minus f of a. So this is the limit as h approaches 0 of f of a plus h minus f of a all over h, where a and f of a come from the given point. So this is like saying a equals 1, and f of a is plugging 1 into our function, and in this case it's also 1. So that would be like 1 plus h minus f of 1 all over h. So f is x squared. So that's 1 plus h squared minus 1 all over h. FOIL your 1 plus h squared. Then clean it up algebraically. And we see, in fact, using algebra, that the slope of the tangent is equal to 2, and that our predicted equation actually matched our original, because you'd have y minus y1 equals 2x minus x1 to give you the slope of the tangent line. Plugged in as 2, and then the 1 and negative 1 are my given point. We can generalize this, which leads us into actual derivatives for chapter 2. So we could generalize this if we wanted to know the slope at any point. Instead of plugging in a equals 1, we're going to leave a as a. Instead of plugging in a equals 1, we're going to leave a as a. So the slope of the tangent would be equal to the limit of the slope of the secant and all you're going to do now is treat f of x equals x squared and find the general slope of the tangent. But leave a as a instead of making a a number. So that would be a plus h plugged into f of x. So again, here's my f of x. So your formula says, okay, you're replacing x with a plus h. So that becomes a plus h squared. You replace x this time with a, so you get a squared. So that's where that equation came from. Now you're going to FOIL. So a plus h times a plus h is a squared plus 2ah plus h squared. Because first, last, outer, inner would give you ah twice. Clean it up. A squared minus a squared cancel. You can cancel an h from your numerator and your denominator, because you could take that out as a GCF. Plug in 0. And the slope of the tangent line to the function y equals x squared at any point is 2a. So again, this represents the slope of the tangent to x squared at any point a. So if you want to know like what the slope of the tangent line at 10 was, then it would be 20. If you want to know the slope of the tangent line at -1 was, it would be -2. Because all you would do is plug in a value for a, and that would tell you the slope of the tangent. I promise we're going to keep doing tons and tons of problems like this tomorrow.